Here's another video to the lecture Intro PDE. In this lecture we present section 3.5. This is the last section of chapter 3 and it's quite short. We present Dirichlet's principle. Dirichlet's principle gives another characterization of the solution of the Dirichlet problem, and this other characterization gives also a method to construct the solutions of Dirichlet's problem. So this is a very nice principle which also has generalizations to many other problems. So this is an interesting method by itself, to construct solutions by variational problems. Okay, now let's state what is Dirichlet's principle. Let omega be bounded and open, and the divergence theorem should apply. So it should have enough regularity such that the divergence theorem applies. We prove this if the boundary is a submanifold, so means a C1 manifold, but C1 submanifold, but the divergence theorem is true in many other and more general situations, and then this Dirichlet principle can be also applied. Now, for a continuous real function on the closure and G on the boundary, we have two continuous real functions. The solution of the Dirichlet problem is the minimizer of the following functional. So the functional is this expression. It's an integral over W. So functional means we have a space of functions and associate to any function a number. This means a functional. So we define on a space of functions numbers, so real functions, and this we call functional. And so we associate to the function W, which should be twice continuous and extends with all partial derivatives up to order 2 to the closure of omega. And on the boundary, it should be equal to G. Then the functional is this expression. So it's an integral over the square of the gradient minus W times F, and we integrate this over the domain. Okay, now we remark, in the functional itself, in the expression of the functional, only F shows up. The dependence on G is put in the domain of the function. We consider functions which take on the boundary the values which are given by G, and the inhomogeneity we put in the functional itself. So we have to prove that this is a minimizer. So if it solves the Dirichlet problem, then it's smaller or equal to I of W for any other W in this domain. Okay, now let's assume U is a solution of the Dirichlet problem and W is another function in the domain. Then we have to prove. That E of W is larger or equal to E of U. This we now have to prove, because we want that this is a minimum. The solution of the Dirichlet problem should be a minimizer, so it should give the smallest possible values. So this means a minimum in this infinite dimensional space. Okay, so we first do an integration by parts. We have clearly this is 0 in omega. So if we multiply this by this, then this is also 0, so this is 0. Now integration by parts means, of course, here we want the second term we don't change. We only change here this first term, yeah? And so we have minus Laplacian u times u minus w. And we want to put minus Laplacian u. So to which function we should apply the divergence theorem? Clearly, this is divergence of minus gradient of u times u minus w. Yeah, if we calculate this, then we first get minus Laplacian u times u minus w. So this is the term which we have. And here we get minus gradient u times gradient of u minus w. Yeah, so this is the second term. Okay, and so this integral over the domain, yeah, this integral here, so the first part over the domain is equal minus this term, yeah, which is here the negative of this term, is equal to the boundary term. Yeah, but what is with the boundary term? Yeah, u minus w, sorry, vanishes at the boundary. Yeah, so we get no boundary terms in the divergence theory. So we know the integral over this plus the integral over this vanishes. So we really get that the integral over this is the integral over this. This is just this expression here. Okay, and the second term we just we didn't change. Now we have this formula. Now we use this formula to transform this. Now we take this. Yeah. So this is not the functional. It differs here by a factor 1/2. Yeah. Okay, but let's take this function. Now here we have this one term we have here inside, and clearly we have. So if we multiply this out, du times d of u minus w minus f of u minus w. If we multiply this out, what we get? Then we get du times du minus du times dw minus fu plus fw. So the integral, this integral here, this vanishes. So we have, if we take all these integrals, they vanish over omega. Yeah, so this term and this term together gives us this term. And if we bring this to the other side, then we get this term here minus this term here, yeah, on the other side. So we get this term. So this equation here implies this equality. Yeah? This equation here, that this is 0, is nothing else but this equality if we multiply this out. Okay, so now we have this equality. And now we use Cauchy-Schwarz inequality. Yeah, look at this term. This term, we can really write at this term plus the square, plus an integral over a square. This is clearly non-negative. So this is clearly larger or equal than this, yeah, because these are non-negative functions here. Yeah, these are sums over squares, so these are non-negative functions. Now, if we multiply this out, yeah, 1/2 over gradient u minus gradient v times gradient u minus gradient w. This is, of course, yeah, here we get 1/2 over gradient u square plus 1/2 over gradient w square. And what are the mixed terms? We get gradient w times gradient u with a minus, and the same here, reverse, but it's abelian, so we have minus gradient u, gradient w. So, okay, and if we insert this, if we, then you see, this term cancels with this term, and we just obtain, it just remains these two terms here. These two terms here. So we have that this term is smaller or equal to the sum of these two terms. Now if we insert this here, so this is exactly this term. The second term we have here again, and then we write it in this form. So this term and this term we add, this term we add with this term. So we have this term. Now observe, this is clearly this term here is the functional evaluated at w. This is the functional evaluated at w. But here, this we can bring to we can subtract from the left hand side, and then we see indeed this formula implies, so we really get that u of u is smaller or equal e of w, the functional. So, and since this is true for any other element, we made no assumption, so this is true for any other element. We really see that that it's a minimum. So we really see it's a minimum. By the way, one can use this. It can be only equal, if this here is 0, if this expression is 0, and this can be only 0 if this expression is 0. So it can be only equality. Equality can only show up for gradient u, sorry, gradient, not, so can only show up gradient u equal gradient w. So, or equivalently, gradient of u minus w is 0. So this means u minus w is constant. And since u minus w is equal to 0 on the boundary, this really implies u is equal to w. So you see, by this argument we also get uniqueness. Okay, so we have shown that it's a minimizer, and we have even shown uniqueness. Okay, now conversely, we assume that u is a minimum of I of the functional. Okay, then now we take u plus tv, for all real t's. But we want that this function really belongs to the domain. We want that this belongs to this domain. In order that this belongs to this domain, we need, if v at the boundary vanishes, then they all belong to the domain of I. Okay. So we assume that it vanished on the boundary, then it's fine, and we can insert this, and then it's clear. We have now we just calculate this function by linearity. We see this is a polynomial with respect to t of second order. Since u is a minimum, it must be that the linear term vanishes, because it's a minimum. So the linear term vanish, because otherwise this is not a minimum for t equals 0. This real function depending on t must be minimal for t equals 0. So this term has to vanish. The derivative has to vanish. So this vanishes. This vanishes here. This is just this term here. And now we claim that this is the same as this. Here we do again a partial integration. If we use gradient of divergence, of gradient u times v, then this is clear. This is Laplacian u times v plus gradient u times gradient v. Now now we want to apply divergence theorem to this term, to this vector field. V vanishes on the boundary, so we get no boundary terms. This vanishes on the boundary, so we have no boundary terms. So the integral over the domain is 0, since we by the divergence theorem. And so we may this expression we have, so this is the same as the negative of this expression here. So we obtain this. Now we can factor out v. So we see this vanishes, and this is true for all functions with this property. For all functions with this property, this here vanishes. So this expression vanishes. But then now we can again apply this argument which we had before. Since v is continuous, if this is at any point non-zero, inside of omega, then we can find a function v which is on an arbitrary small ball around this point, positive, and has support in a small ball. And we can choose this ball so small such that this expression is on this ball either only positive or only negative. If this is at any point non-zero, by continuity, it's continuous. So then this integral cannot vanish for all these functions. So we really get by this last equation that this has to be 0. So we get that this really solves the Dirichlet problem. And u belongs to the domain, so it completely solves the Dirichlet problem. And this shows the reverse. This remark we already explained. We also get uniqueness. And this Dirichlet principle can be used to construct the solutions. If we can show that this variational problem has a solution, has a minimizer, then we know that this minimizer has to be a solution of the Dirichlet problem. So by showing the existence of a minimizer, we get solutions. And this indeed can be carried out. Okay, so what we have done today, we introduced this Dirichlet problem. So we showed that the solution of the Dirichlet problem is a minimizer of an appropriate function. And that we also showed that the minimizer, any minimizer of this functional, is a solution of the Dirichlet problem, and we even showed that the minimizer is unique. Okay, thank you.